Pluto is miles off and a diffused, extra-accepting planet that was once a part of our nearby planetary system. However, startling statements by fundamental astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight. They suggested that this far-off world is on a potential collision course with Neptune. But how could this actually happen? Furthermore, what could be the consequences of such a massive event? Are we witnessing a troublesome, unconventional cosmic event? Or is there another explanation for this approaching near-catastrophic disaster? Join us as we examine the plausible results of a Pluto-Neptune collision. Pluto, a former planet that was reclassified as a dwarf planet, remains a subject of interest in the study of the vast universe. According to recent speculations by leading experts, Pluto's orbit dangerously approaches Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potential collision between these two planets, which could pose a significant risk to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit. Since its discovery in 1930, Pluto has yet to complete one full revolution. However, the story doesn't end there. Pluto's orbit is marked by its exceptionally elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more remarkable is its inclination, which is 17 degrees to the ecliptic plane. The way Pluto follows its path is highly eccentric compared to other planets. This inclination and eccentricity add layers of complexity to its orbital dynamics. One of the most fascinating aspects of Pluto's orbit is its interaction with Neptune's. For about 20 years in each orbit, Pluto comes closer to the Sun than Neptune does, defying the expected order of their positions in the planetary system. This raises the obvious question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of various planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers attempted to understand its unique path. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stands out with its steep inclination and irregular shape. The mystery deepened with the realization that Pluto's orbit indeed crosses Neptune's. The stability of Pluto's orbit, despite these complexities, is evidence of the intricacies of celestial mechanics. The three-body problem in space involves determining how three objects, like Pluto, Neptune, and the Sun, move and affect each other with their gravity. It's like trying to predict their positions based on where they started and how they interact. In Pluto's case, this problem reveals how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complex manner. The terms non-synchronous libration, orbital precession, and VZK wobbling are key to understanding this enigma, as described by astrophysicists. Non-synchronous libration ensures that when Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from overlapping. Orbital precession refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other massive planet, it is positioned far above their orbital plane, adding an extra layer of safety from potential collisions. Another key aspect of the situation is VZK wobbling, named after three scientists, VZ Kai and others, who studied how objects move in space. This wobbling involves how three space objects like Pluto, Neptune, and the Sun pull on one another with their gravity. This gravitational interaction influences their movements. In Pluto's case, VZK wobbling helps us understand why its orbit near the Sun is so unpredictable. Despite appearing chaotic, this wobbling ensures Pluto's orbit remains stable over extended periods, preventing collisions with Neptune or deviations from its path. The VZK wobbling demonstrates that, despite the seemingly chaotic nature of space, patterns and rules maintain some control. These forces help keep Pluto's orbit stable, ensuring it doesn't collide with Neptune or veer off course. This three-body problem is central to understanding how these orbits evolve and change over time. Despite the complex dynamics of Pluto's orbit, astrophysicists emphasize that the chances of an actual collision with Neptune remain astronomically low. The reason lies in the synchronized gravitational dance between the two celestial bodies, which has been maintained for millions of years. This gravitational resonance ensures that their orbits never intersect at the same time and place. However, if such an unprecedented event were to occur, the consequences would be monumental, not just for Pluto and Neptune but for the entire solar system. The sheer scale of the collision would release unimaginable energy, potentially disrupting the orbits of nearby celestial objects. Such an event could even trigger a domino effect, altering the delicate balance of gravitational forces that govern our solar system. One of the most critical questions is how this could impact Earth. While our planet lies far from Pluto and Neptune, any significant disturbance in the outer solar system could potentially send shockwaves inward. For instance, asteroids or comets from the Kuiper Belt, a region of icy bodies beyond Neptune, could be dislodged and sent hurtling toward the inner solar system, increasing the likelihood of impacts on Earth. Astrophysicists are also exploring the possibility that such a collision could lead to the creation of a new celestial body. The debris from a Pluto-Neptune crash could coalesce under the influence of gravity, forming a new dwarf planet or moon. Alternatively, the collision could scatter material across the solar system, adding to the already vast field of cosmic debris orbiting the Sun. But why are scientists raising these concerns now? Advances in observational technology and computational modeling have provided deeper insights into the long-term behavior of celestial bodies. Sophisticated simulations allow researchers to predict potential orbital instabilities millions of years into the future. While the models suggest that Pluto and Neptune are unlikely to collide, the mere possibility highlights the dynamic and ever-changing nature of our solar system. For now, Pluto and Neptune continue their intricate dance, guided by the unseen hand of gravitational forces. Their orbits, though seemingly chaotic, are governed by laws that have kept them in harmony for eons. Understanding these celestial mechanics not only deepens our knowledge of the universe but also reminds us of the delicate balance that sustains the cosmic order. In conclusion, the speculation about a Pluto-Neptune collision serves as a fascinating reminder of the complexities of our solar system. While the likelihood of such an event is exceedingly small, it underscores the importance of studying celestial dynamics and preparing for the unforeseen. As our knowledge of the universe expands, so too does our appreciation for the intricate forces that govern it. Because of the manner in which space objects pull on one another, concentrating on this assists us with more deeply studying Pluto, our nearby planetary group, and, to be sure, even far-off worlds and their stars. Numerical reenactments in the late 1980s revealed that, regardless of the stabilizing properties of Pluto's orbit, it is genuinely unpredictable, with minor deviations in starting circumstances leading to enormous variations over millions of years. However, these characteristics of Pluto's orbit have been found to maintain stability over generally prolonged timescales. Examining the disturbances from recent automated probes has helped us understand how the giant planets like Neptune, Jupiter, and Saturn affect Pluto's orbit around the Sun. Neptune has a remarkable relationship with Pluto, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This relationship maintains Pluto's orbit as stable. Yet Neptune is not the only planet at work. Jupiter's gravity also plays a critical role in stabilizing Pluto's orbit, and Saturn contributes as well. These studies show that Jupiter's massive gravity is strong enough to ensure Pluto remains on a stable path for an incredibly long time, possibly even for an extended period. So, perhaps Neptune, Jupiter, and Saturn are coordinating to ensure Pluto continues moving smoothly through space without running into trouble. These eccentricities are crucial for maintaining everything in place. Without these elements, the planetary system, as we know it, would be much harsher. Bodies like Pluto could collide with others or be ejected from their stable orbits, triggering a chain reaction with other celestial bodies. For Pluto specifically, with discussions about it potentially colliding with Neptune in the future, understanding its orbit is imperative. This gives us a clearer picture of the dynamic nature of the nearby planetary system. The case of Pluto demonstrates that even the most seemingly unstable orbits can reach a state of harmony through the complex interaction of gravitational forces and orbital mechanics. It also highlights the significance of continuous observation and investigation of these quirks to better understand our place in the universe. Exploring the depths of space often compels us to confront the extraordinary nature of celestial bodies. Pluto's orbit is a great example of this phenomenon. The theory of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is vividly demonstrated by Pluto. This means that even slight changes in the dwarf planet's position or velocity can drastically alter its long-term orbit. Using digital simulations has been immensely helpful for researchers in understanding how Pluto moves in space. These simulations use complex mathematics to model how Pluto and other space objects like Neptune pull on one another. By tweaking small details in the simulations, space scientists can see how even minute changes can make a huge difference in where Pluto ends up. In the late 1980s, those simulations revealed something intriguing about Pluto's orbit. Despite having features like asynchronous libration and orbital precession to keep it stable, its orbit can still be inconsistent and strange. If you start with just a small difference in where Pluto is or how fast it's moving, its orbit could end up looking completely different after just a few years. Yet despite this chaos, Pluto's orbit remains stable over large time scales, like billions of years. This suggests that Pluto's journey around the Sun has a kind of order to it, even though it seems wild at first. Predicting celestial actions, especially when they involve irregular orbits like Pluto's, is a massive challenge. The inherent unpredictability of these patterns means that long-term forecasts are often filled with uncertainties. While mathematical models provide excellent tools for understanding and predicting the future movements of celestial bodies, they also highlight the limitations of our predictive capabilities. These models heavily rely on the accuracy of initial conditions, and any small errors or distortions can lead to vastly different outcomes, making precise predictions a daunting task. Beyond the chaotic nature of planetary orbits, Pluto reminds us of the ever-changing and dynamic nature of the universe. Although we've made great progress in understanding space, Pluto's case serves as a reminder of how much our knowledge of the universe still remains limited. Grasping the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the planetary system. It shows how the presence and role of each planet can significantly influence the balance and trajectory of other bodies in the system. So why are leading astrophysicists now raising concerns about a potential collision between Pluto and Neptune, despite all those complex forces working to prevent such an event? Neil deGrasse Tyson, a prominent astrophysicist and a key figure in advancing cosmology, offers a unique perspective on the mysteries of our solar system, specifically the fascinating case of Pluto. Tyson, known for his role in reclassifying Pluto from a planet to a dwarf planet, provides insightful analysis on the evolving nature of celestial mechanics and the public's interest in the overlooked corners of space. Tyson's role in Pluto's reclassification is based on the ever-expanding understanding of our solar system. He views the reclassification not as a diminishment but as a significant adjustment to our growing knowledge of the various bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits like Pluto's as a reminder of how much there is still to discover in space. The fascination with these questions keeps the exploration of space so exciting. Yet, despite Tyson's optimism, his thoughts on Pluto's potential collision with Neptune paint a different picture. His concerns about the future of Pluto's orbit suggest that we may still have some mysteries to uncover. Tyson's concerns about Pluto's orbit reflect the inherent uncertainties in understanding celestial mechanics over vast timescales. While the relationship between Pluto and Neptune currently ensures their paths do not cross, even small changes in the gravitational interactions between celestial bodies could alter their future trajectories. These changes may take millions, even billions, of years to manifest, but they highlight how delicate the balance of our solar system truly is. One of the most remarkable aspects of Pluto's orbit is the intricate interplay of resonances and gravitational forces. Neptune's 3:2 orbital resonance with Pluto is a stabilizing factor that prevents close encounters between the two bodies. However, the influence of Jupiter and Saturn adds further complexity to the equation. Their combined gravitational forces help anchor the stability of the entire solar system, but even slight shifts in their positions could ripple across the orbits of smaller bodies like Pluto. Astrophysicists have long used Pluto as a case study to explore the principles of orbital chaos. The simulations conducted in the late 20th century laid the groundwork for our understanding of how seemingly stable systems can harbor chaotic elements beneath the surface. Today, advances in computational power allow researchers to model these dynamics with greater precision, uncovering new insights into the forces that shape our solar system. Yet, despite these advances, our understanding remains incomplete. The possibility of a future collision or drastic orbital shift, whether for Pluto, Neptune, or other bodies, remains a reminder of the limits of our knowledge. It also underscores the importance of continued observation, simulation, and exploration. Missions like New Horizons, which provided unprecedented data on Pluto, are vital for expanding our understanding of the outer reaches of the solar system. Pluto's story is also a human one. Its reclassification as a dwarf planet sparked public debate and reignited interest in astronomy. It reminded us that science is not static. It evolves as we learn more. Tyson himself has emphasized that the decision to reclassify Pluto was not about diminishing its importance, but about refining our understanding of what defines a planet. As we look to the future, the study of Pluto and its orbit will remain a rich field for discovery. By examining the interactions between Pluto, Neptune, and the giant planets, scientists can gain deeper insights into the forces that govern not only our solar system but also planetary systems around distant stars. These investigations could shed light on the origins of stability and chaos in the universe, helping us to better understand the conditions that allow planetary systems and life to thrive. Ultimately, Pluto serves as a reminder of the complexity and beauty of the cosmos. Its orbit, while seemingly chaotic, is a testament to the intricate dance of gravitational forces that shape the universe. The mysteries it holds challenge us to keep exploring, to keep questioning, and to keep pushing the boundaries of what we know.